Okay, easy. We secretly coordinate the vertex labels.
That is...
Maybe the Bay resuspect cheating.
Here we have two graphs, G and H. They look different geometrically, but graph isomorphism does not care about the drawn representation. So the question is, can we relabel the vertices of one graph to obtain the other? Now we define a mapping. 1 maps to A, 2 maps to B, 3 maps to C, and 4 maps to D. This mapping is a bijection, meaning every vertex is matched uniquely with another vertex. Notice that every edge is preserved under this relabeling. So even though the drawings look different, the underlying graph structure is the same. That means the two graphs are isomorphic. Next, we translate the problem into linear algebra using adjacency matrices. The matrix, P, is called a permutation matrix. It simply rearranges the vertices. And the key condition becomes A sub GP equals PA sub H. So graph isomorphism reduces to finding the correct permutation matrix. Keep this equation in mind because it will reappear in the quantum version later. This is the graph isomorphism game. We take two graphs, G1 and G2. G1 is a path on 5 vertices. G2 is a star with 1 center and 4 leaves. They have the same number of vertices, but very different structure. In fact, their degree sequences already show they are not isomorphic. Now we turn this into a game. There are 2 players, Alice and Bob, and a referee. Alice and Bob agree on a strategy before the game starts, but after that they cannot communicate. The referee sends each player a vertex from the graphs. Each player must respond with a vertex from the other graph. They win if their answers preserve the structure. Adjacent vertices must map to adjacent vertices, and non-adjacent vertices must map to non-adjacent vertices. In the first round, both players receive the same vertex, so they just output consistent answers according to their shared plan, and this round succeeds. In the second round, the referee sends 2 adjacent vertices from G1, so the relation is adjacency. But when the players map these vertices into G2, the corresponding vertices are not adjacent. So the structure is not preserved, and they lose. In the third round, the referee sends 2 non-adjacent vertices. This time, the players again respond consistently, and non-adjacency is preserved, so this round works. But the important point is that a single failure means the strategy does not work. The underlying reason is structural. G1 has degree 2 vertices, while G2 does not. So any bijection between them must break adjacency somewhere, and the referee can always exploit that. So we conclude, a perfect classical strategy exists if and only if the 2 graphs are isomorphic. Here they are not, so classical players must fail.
What if 2 graphs were different, but quantumly the same?
Yeah, we're going there. Before the game starts, players share entanglement. It's a linked system, no matter how far apart. It doesn't let them send messages, but it lets their answers be connected in a way classical systems can't replicate.
Quantum isomorphism means, can 2 players convince a referee the graphs match in this interaction game?
Now we introduce the quantum twist. Before the game starts, Alice and Bob share an entangled quantum state. This is a single joint state, distributed across both players. After this point, no communication is allowed. All correlations must come from this shared state. But in the quantum version, a strategy is a collection of measurement operators, projection operators. For each possible question X, Alice has a set of projectors E sub XA, and Bob has a corresponding set F sub YZ. When a question arrives, they perform a measurement, and the outcome is probabilistic. Now consider a specific round. Alice receives vertex 2, and Bob receives vertex 3. They each perform a measurement on their respective halves of the entangled state. From Alice's perspective, the state looks like a superposition of possible answers. Each possible output has an associated probability amplitude. When she measures, the state collapses. One outcome is selected, in this case, vertex B. Bob's system collapses simultaneously. Even though no information is sent, his outcome becomes correlated with Alice's. He obtains vertex C. The important feature is that these measurement operators are not arbitrary. They must satisfy consistency rules, orthogonality, completeness, and no signaling between Alice and Bob. Now we move from classical symmetry to its quantum upgrade. In the classical case, symmetry is described by a permutation matrix P, but quantum theory generalizes this idea. Instead of permutations, we use unitary matrices, denoted U. Now the entries are not just zeros and ones, they are complex amplitudes. Each entry behaves like a projection, and the constraints are preserved in a stronger sense. Unitarity replaces row and column sums. So what we had before as a rigid relabeling becomes a continuous transformation in a complex vector space. And the key point is this correspondence.
Non-isomorphic. Different degree sequence, different structure, classically not the same.
But give Alice and Brob some entangulation, and they win every round.
Quantum isomorphicy is real. Mernin's magic square proved it.
Graph theory will never be the same.
Now the natural question is, do these kinds of graphs actually exist? The answer is yes. There are finite graphs G and H such that they are not classically isomorphic, but they are quantum isomorphic. In other words, no permutation can match them, but a quantum strategy can still perfectly pass the game. This is a proven mathematical result. And the deeper insight is this. Classically, graph isomorphism is determined by comparing homomorphism counts from all graphs, but in the quantum setting, this changes dramatically. It becomes enough to compare homomorphism counts only from planar graphs. So what changes is not the graphs themselves, but the set of tests used to distinguish them. Entanglement doesn't just improve your chances in certain games. It doesn't just give you better strategies or better correlations. It actually changes the notion of what it means for two structures to be the same. In the classical world, two graphs are the same only if there is a relabeling between them, a strict permutation. But in the quantum world, sameness is defined by what can be achieved through entangled measurements and operator correlations. So graph isomorphism is no longer just about matching vertices. It becomes about matching the deeper structure of observable quantum correlations. And that shift from permutations to quantum strategies is where the real difference lies. Thank you.
I use ChatGPT. I love ChatGPT. I love it. ChatGPT is fantastic. It's so not ChatGPT